co-host,
Okay.
and I'm making you as a presenter also.
Okay then.
Kindly, you can share your slides once.
It's done. Okay. I have shared.
Yes, it is visible, sir. Our screen is coming. You
Okay,
can
sir.
share the slides also. Yes, it is coming, sir.
Okay, sir.
Two more minutes, sir.
Okay, sir.
So, good afternoon, everyone. We have with us Dr. Naresh Raghuvanshi, sir. He is an assistant professor in Department of Mechanical Engineering, MNIT Jaipur. Sir, Naresh Raghuvanshi, sir, has done his MTech from MA Maulana Azad NIT Bhopal in the area of stress and vibration analysis, and he has done the PhD from IIT Indore. Sir has many journal publications, conference publications, more than 5 journal publications, and he has also received the DST International Travel Grant for Young Scientist or Researcher for presenting research paper in VIRM 11 at the University of Manchester, UK, given by Sir DST in the year of 2016. So let us welcome Dr. Naresh Raghuvanshi sir for delivering his lecture on condition monitoring and fault diagnosis. Welcome, sir.
Thank you, sir, for a nice introduction. Yes. Am I audible, sir?
You are audible, sir. Only thing is when the session will start, so
Okay.
after brief introduction, you can will turn off our camera so that
Okay.
their data will be saved.
Okay.
Thank you, sir. I hand over to you, session to you, sir.
Okay, sir. Thank you, sir. Sir, actually, by switching the camera off, there is something missing.
Down there we start video, stop video.
So
Okay.
please click on hide
Okay.
and then you.
Okay. I think it's off.
Yes, sir. Now it is done, sir.
Okay, sir. Okay, so good afternoon, everyone. I am Dr. Naresh Kumar Raghuvanshi, and sir already has introduced me. And now the presentation on condition monitoring and fault diagnosis. And basically, this subject, it is not a topic; it's a whole subject, and it's related to not only the mechanical engineering, but also the electrical machines or other computer science also. The fault diagnosis is also done in other fields also. But mainly I am focusing on the condition monitoring and fault diagnosis for the mechanical machinery, and the basic concept and the basic introduction. So after completing this lecture, you will be able to uh, find the fault in any mechanical machinery. Mainly mechanical machinery is generally combined with the gears, bearing, and these are the main elements generally in the fault occurs. And also in the electrical machines, some current signature analysis also will be done in the field. So mainly the focus on the fault diagnosis for mechanical machineries like rotating machinery mainly. So the bearing and gears I will mainly in the next slide you will see. So the basic introduction of the condition monitoring techniques, and the vibration analysis mainly. So I will explain why the vibration analysis is the uh, main technique to diagnose the fault in the machinery. Then I will explain the gear fault diagnosis, bearing fault diagnosis, and these are the experimental diagnosis methods, and also how to simulate these fault. So the gearbox dynamic modeling also I will cover in this lecture. So before going to detail, some types of machines that is in mechanical or in electrical engineering, you will find it. Some electrical motors, pumps, fan, gearboxes are mainly the components for reducing the speed, converting torque. Okay, in any mechanical machines, you need some gearbox. Also in automobiles like car and vehicles, there is a gearbox, everybody know. But in some also other machines, the gearbox is also required. Compressors, steam turbines, some pictures also I have shown here in the below this one. So this is something steam power plant, thermal power plant. So there is some steam turbines, okay, electric generators, gas turbines, hydro turbines, rotating and reciprocating machines. So these are the basic machines in any industry. So and the fault diagnosis I'm talking about. Actually, first of all, we design the machinery, install the machinery, and after that it is working properly or not, so some maintenance is required in this field. So that's why the fault diagnosis is for the research purpose also, and for industrial engineering, and then they will find some applications in this. So basically, now the next slide, machine condition. So first of all, we design some machine and install in some industry. So proactive doing activities, proactive performance, improvement performance like the lubrication, excellence, precision maintenance, alignment, balance, select suppliers. These are some basic steps which we do the proactive. Means here the machine is not working, but we are installing the machine in any industry for that purpose. So we expect that it is the highest level and equipment performance is highest. Means this horizontal line, the lubrication excellence above the horizontal line, indicating that the performance is highest. Okay, so when the machine is under working condition, then the second step is the predictive. So first is the proactive, that is all engineers do well job for installing the machine and arrange the training from programs, job planning, scheduling, all things, every work have been done. Now the second is machine is running. Okay, so predictive means that the machine is working properly or not. So the first signature, the first analysis technique, that's the vibration analysis. So whenever the small change in the working of the machine, we can predict, we can analyze through vibration analysis. The mechanical ultrasound, oil analysis, thermography, and non-destructive testing. So these in the middle are the predictive maintenance. So these are the condition monitoring techniques basically for diagnosing detecting the fault or diagnosis the fault. So these are the techniques we apply, but in this case the machine is not stopped. Okay, so it's working, machine is working, but we analyze these because these signatures, the machine is working properly or not. Some in the third, reactive maintenance. Reactive means something wrong in the machine. Suppose machine is means the machine becoming hot, so some heat is emitted from the machine. So some maintenance engineer will be there and they think, okay, this is the hot. Suppose we are in computer, okay, in laptop, some heat is come up from there. So we can say, okay, so some cooling is required, or I shut down this laptop. So like that in the machine, some heat, extra heat is predefined. We cross the heat in the predefined. The temperature is rising more than the normal condition of the machine. So we tell the warning machine is not working properly. Feel, if you feel like noise is also a reactive, because the vibrations in the machine means you are not able to sense without some instrument, but you are not sensing that okay, it is vibrating. But if it's vibrating, then obviously some noise will be there. So while analysis the noise, so you can say also the machine is not working properly. Smell, something is wrong. Suppose in electric wires, if it is smelling like something is wrong, some fault is there. So we can say okay, something is wrong in the wire cable. Like that in machine, some oil burning smells is there, or smoke. The third one is smoke. So if the smell in smoke condition is there in the machine, that means your machine will be going to die. Okay, so the machine will stop. Something like something is wrong in the machine. Like in human, okay. So if we are something ill, we go to the doctor, and doctor takes some tests from our blood. Okay, and then we diagnose some disease according to the blood test. So in also in the machine, something that oil analysis. In oil analysis, generally oil is like a blood in the machine. So if we analyze the oil, different faults, different conditions of the machine we can analyze. So these are some basic condition monitoring techniques uh, for maintaining the machine. So the predictive, this is in the middle, predictive maintenance. And out of these predictive maintenance techniques, the vibration analysis technique is mostly used in industries also, because of some means low cost to the earth, or finding the fault at the early stage, just after the good health and something health is wrong, then the vibration analysis will predict to you something is wrong in the machine. So predictive maintenance generally done in the condition monitoring technique. So I hope this chart will give you some over idea about the machine condition. Okay, so what is the condition monitoring? Condition monitoring is the process of monitoring a parameter of condition in machinery. If we are monitoring some parameters, the parameters may be the vibration, some parameters may be the temperature of the machine. Okay, so some noise is also in the machine. So some parameters we are measuring. Okay, so this is the process, and it is a major component of predictive maintenance. So the predictive maintenance in earlier slide, this is the predictive. Okay, so these are some techniques we will discuss here, the vibration analysis mainly, but you know there is some basic concept about the other techniques. Okay, so the use of conditional monitoring allows maintenance to be scheduled, means at what time we will do the maintenance in the machinery. So with the help of condition monitoring, we are monitoring the parameters at regular intervals or in a continuous time. So we can schedule what time the machine we will stop, and then maintenance will be done, and after that open there. And other actions to be taken to avoid consequence of failure. Okay, so obviously if we are not maintaining that machine, the failure will be occur, and some catastrophic failure also will be there. Fault diagnosis. So fault diagnosis basically comes under the condition monitoring and fault diagnosis. Basically, we are doing some fault analysis. Fault detection is also one word. Something is a fault detection and fault diagnosis. Okay, so we will see here a fault. A fault is another, we can say, the problem. Okay, if the machine has a fault, means something is problem in the machine. Okay, so fault diagnosis means something we are analyzing some problem. So what is the problem in the machine? They're not working, not reliable. Okay, so not working properly, that means something is wrong in the machine. So a fault or problem does not have to be the result of a complete failure. Earlier, I have also explained that it is not necessary that the machine is completely failed. Okay, fault is something, problem is there. Okay, but machine is under working. Fault, fault detection is just recognizing that a problem has occurred. If some problem is there, that means if you detect some problem, that means fault detection is in this category. Even you don't yet know the root cause. You don't know what is the reason for this fault, for this problem, but you detect something is wrong in the machine. Okay, but if the root cause we will find out or isolate that fault, that is in the category of the fault diagnosis. Okay, so fault may be detected by variety of quantitatively or qualitatively means. Okay, fault diagnosis is pinpointing one or more root cause of problem. So, and then corrective actions will be there. If you find that the root cause, suppose in human beings also, doctor is find okay, so something is problem in your blood or blood sugar is high, something. So they know the root cause for that, and they prescribe some tablets for the use. So like that in the machine, if you find some root cause, what is the problem in the machine, then you will do something accordingly. Okay, so the maintenance engineer will know about these what they will correct so that the machine will work properly. This is also referred as a fault isolation, especially influence for distinguish from the fault detection if we consider. Otherwise, the fault detection and fault diagnosis we can say the same thing in the condition monitoring technique. Okay, so in the next slide, condition monitoring techniques. Wide range of condition monitoring techniques is available in the industry. Some are basically I highlighted also here: the vibration analysis, oil analysis, beer debris analysis, thermal analysis, ultrasound analysis, and many more. Vibration analysis, I will explain means each and everything. So after completing this course, we will be able to analyze the vibration analysis for the machine, and we will find out okay, this machine has a fault and where it is for where is the location of this fault, what part of the machine it has. Okay, so we will discuss in the vibration analysis. Oil analysis, generally every machine, if a rotating parts is there, gears or bearings, okay, or shaft in the bearing, oil is there. Okay, so it means reduce the friction between the two surfaces. So the analysis of oil, how we will find this for something, suppose uh, some particles, some foreign particles will be there in suppose in the gearbox. Okay, so that oil after some working of the conditions, the oil degraded. Okay, so initially the oil is okay when you filling the, and after that it's like a black oil. Okay, so you analyze the whatever the foreign particles come in the oil. Suppose if the where tooth is there, if tooth is missed, and it will fall down in the oil. So we analyze, and some foreign particles or gear tooth may be there in the, so we can say okay, so gear tooth is missing in the, that's why the condition of the gearbox is very critical. Wear debris analysis also, some wear debris means some that's the particles I have explained. So some magnetic some magnets are used, so they detect some, suppose iron is there, then they attract these particles. Okay, so that these wear debris analysis in broad way, you think the different size of the wear debris. Okay, so something is there, and separate one chapter is there for this. Thermal analysis, I have told in some thermography, thermal camera is also there. They detect how the machine is, temperature is rising in that machine. Okay, so thermal analysis, ultrasound analysis also you can do. Ultrasound sound is coming from this, and you can analyze. So these are some techniques and many more. Okay, so but I'm focusing on this vibration analysis. Vibration, generally, if you are belonging to the mechanical engineering, then you know the vibrations also. But in also in electrical engineering, many the simple terminology of the vibrations everybody know. I think vibration can be defined some mechanical oscillations about an equilibrium position of a machine or component, okay, or simply a back and forth motion of a component. Some basic advantage of the vibration is what? Generally, you consider the vibration is means the vibration has some disadvantage because due to vibration, the noise will be coming out and the machine will fail. But uh, if you are capturing the vibration signal, you will find the fault in the machine. That is the advantage of the machine. If the vibration is not coming, then this technique we cannot apply for the other fault analysis. So the vibrations produced in the machine are the best indication of the machine health. So, we can say the benefit of the vibration. Vibration monitoring can alert us to so many different conditions that may indicate potential machine failure. Something unbalanced will be there, misalignment of the shaft is there, or the whole machine, gear wearing fault, resonance conditions, looseness in some fixtures, okay, nut and bolt, something else there, cavitation generally in the pumps will be there, electrical problems. Okay, so these are some things which we can monitor with the help of vibration analysis. So in the next slide, what we measure for vibration analysis. Okay, so vibration analysis, but what we are measuring in the vibration analysis? So basically three things, something amplitude maybe of the displacement of the vibrating body, or the velocity of the vibrating body, or the acceleration. So these are the amplitudes we can means, if we talk about something, the graph is between amplitude and time. The amplitude will be means maybe the displacement, velocity, or acceleration. For your convenience, what you want to draw for the proper analysis. Second thing, the frequency. How often the movement occurs, that is the frequency. And in the frequency, I will explain why the time domain and the frequency domain. Okay, so some frequency is also required to diagnose the fault. Okay, so basically we are measuring amplitude, frequency, and phase. Phase is just in what direction the movement is given. Okay, so suppose in the rotating machine. Okay, so the directions, in what direction the vibration is occurring. Suppose in X, Y, or in Z. So the phase will be there. And something these the graph are shown here. Okay, so in time domain, you will see some simulated signals are here in the picture, but in actual practice, these type of beautiful, good looking signals are not there. This is the simulated signal. Okay, but in actual condition, we will see in the some next slide how the actual signals of the vibrating board, vibrating machine will be there. So in time domain, some amplitude on the vertical axis and horizontal axis some time. And in frequency domain, you transform this time domain signal into the frequency domain. So you will see how many frequencies, the signals of how many frequencies are involved in the time domain signal, and separate the frequencies. with their amplitude. Okay, so these are the things we will measure. So how you will measure the vibration? Okay, so displacement you are measuring, or velocity you are measuring, or the acceleration you are measuring. Okay, so generally the most useful the transducer is the accelerometer. Accelerometer generally used for measuring the accelerations of the machine, and the many industries also uh, focusing on this because generally acceleration of once you measure the acceleration, you can convert it to in the velocity or in the displacement, because in the velocity acceleration is d2x upon dt square. Okay, if you once integrate it, so this will be dx upon dt, that is the velocity, and once again you integrate it, so it is dx, so this is the displacement. So once if you are measuring the displacement, you can further convert into the velocity or acceleration, or if you are measuring the acceleration, so with the help of some software you can convert these signals into other velocity or velocity or displacement amplitude. Okay, so these are the transducers, and three axis and single axis. These two images are found here. What it means? Single axis. That means you are measuring the vibration in single axis direction. Suppose the horizontal direction you are measuring the vibration, or in the vertical direction you are measuring the vibration, or in horizontal also in two directions, or any orientation. Okay, but a single axis, that means at one time you are measuring the vibration in single direction. In three axis accelerometer, at the same time you place this accelerometer on your machine, so the vibration in three axis at the single accelerometer you can get. Okay, so this is the instrument we will require for measuring the vibration. Now the second thing, you have a accelerometer, okay, but how you place this, how you orient. If this is the single axis accelerometer, then you have some problem that how you will place this. So in axial direction, so this is green. This is the housing, and something in between this is the shaft. Okay, so in the shaft direction, you have to place in the axial. Something is journal bearing is there. So the shaft actually, if movement is there, so you can access, you can record the data in the axial direction. In the middle, the vertical is very simple. If you are not know about the orientation, first of all, think if you have a accelerometer, you will put on the top of the bearing house. Okay, so this is the vertical state. But if you have a three axis, then this single orientation you will get in three directions. And in horizontals, we have to put here. Okay, so some glue is there for fixing this accelerometer on the machine, because machine is vibrating. Okay, so you have to fix this accelerometer on the machine. So some glue is required. Mounting direction, and another image you can see how you will mount this. So some electric motor is there. Okay, horizontal, vertical, and axis. And in the right hand, this is the bearing. Okay. If you are from mechanical engineering, you will know the bearing how it looks like. Okay, so this is the bearing, and these are the three axes for the measuring the vibration. Right. Okay, so there is a accelerometer for capturing the vibration signals, and how from machine to the display of the signals, and for analyzing the what is the fault is there is or not. Okay, so some flow chart I have given here for the vibration analysis. Some machine in the top, so the machine is there. Okay, so vibration signals will be there in the machine. Whether fault is there or not, the vibration signals will be there, because the vibrations we cannot completely removed from the machine. Okay, so some unbalanced forces are there. So machine is vibrating. Okay, fault is there, then it will obviously will vibrate. But if fault is not there, then also the machine will vibrate. Okay, so and the third, machine measuring point. This is the critical point, and also some research papers is also there where we have to put the accelerometer on the machine. Okay, machine measuring point, that is it. So where we have to put the machine. Some orientation on the previous slide I explained you. The some three directions is there. Suppose you are capturing the bearing vibrations. So the bearing housing, you put the vibration accelerometer on the top of the bearing house. If some gearbox is there, so you can put accelerometer on the housing of the gearbox. I will show you in some next slide some picture of the machine and also the placement of the accelerometer. Okay, so accelerometer transducer generally capture the vibration in the analog form. Okay, so some data acquisition system will be there. So it will convert the digital form. Okay, analog to digital converter. The electrical people is very well known how to convert these electrical signals into the digital form. Okay, so some sampling frequency will be required for this purpose, how you are sampling the signals. Okay, so some Nyquist theorems will be used. Okay, so then the sampling frequency should be two times of the maximum frequency of the analog signal, so that some aliasing problems will not be there. Okay, when we back to the analog signal. So some these are some electrical portions after capturing this analog signal. Okay, so in the digital form, so vibration signal analysis. Then you have a some deck card. After that, you have some vibration signals, maybe in the displacement form, velocity form, or acceleration form. Okay, so generally it's in time domain or frequency domain. Means the signals changing in the time, the horizontal axis on the timeline, and vertical axis some amplitude. And in frequency domain, on the horizontal axis, the frequency will be there, and on the vertical axis, some amplitude will be there. Amplitude for the acceleration or displacement. Okay, so by analyzing these time domain or frequency domain, it decides some advantage of the time domain and frequency domain. Some disadvantages also there. Okay, so after knowing very well the which domain we have to consider for the analysis. Okay, so failure analysis, after that we will find the fault. So this is the electrical engineering portion. Some signal processing will be there. Okay, so then display some result, and you basically you compare the healthy machine signals and faulty machine signals. So some changes will be there. So whether in the time domain or in the frequency domain, okay, you will differentiate. It will be healthy and faulty. So these are the basic concepts. So this flow chart, I think we will show the how you are doing in the fault diagnosis, how you are measuring the vibrations, how you are displaying the fault in the machine. Okay, this workshop is also on this LabVIEW programming. So if you are considering, suppose here some data test card is there, so you have to some graphical programming is there in the LabVIEW. So I just explain the overview of this. some complicated screen is coming here. But in the previous few lectures, I think you are well known how the LabVIEW programming is done. Okay, so some deck assistant and filtering, signal filtering, something you have to put here. Then connect it some spectral measurement. Second thing. Third, after capturing the signals, okay, some speed detectors you can apply, or some maximum value or power spectrum analysis you can apply. After that, how to measure the file. So some amplitude or frequency domain and multiple graphs you can plot here. So this is not a hit and trial method, but use properly upon what you need. Okay, capturing of the signal is okay. Okay, after the capturing the signals, what type of display of the results you are going to. So accordingly, your LabVIEW programming you will write. Some filter is also required. Suppose you are denoising the filter, some filter you can put in the programming. Okay, so this is the overview, and you will do you on. Okay, so after this programming, you will get the vibration signal. Okay, so after getting the vibration signals in the time domain or frequency domain, okay, after this programming, then you apply some signal processing techniques. Okay, so in LabVIEW also you can do for this, or in the next slide, this is some software based. I have also worked on this software, the vibration analysis. Some Oros company is there. So some FFT analyzer is here. I think 4 channel. I think is this. And three transducers are given here: microphone, accerometer, just small thing, impact hammer, and some software in your laptop. So this will do no in this system, in this software. Okay, so the LabVIEW is not required, but it costs highly. This software if you purchase for the vibration analysis. Okay, so if you are doing with the help of LabVIEW, then LabVIEW software is required. Okay, and some oscillometer, impact hammer, or whatever the signals you are capturing. So LabVIEW program accordingly you can do. Okay, so this is something related in like a software. You can apply some filters. You can analyze the signal in time domain or in frequency domain. Okay, so on the screen, and you can save these figures. Okay, you can highlight at what frequency, what amplitude is there. Okay. So in the same thing in LabVIEW also, but I think in LabVIEW little less costly. Of this system. Okay, so some bits about the signal processing techniques. In signal processing technique, I have already explained that time domain analysis if is the most suitable technique. If just capturing the time domain, everybody know. Okay, this is the time. This is the amplitude of the velocity or acceleration or displacement, and by showing by seeing the result, you can say, okay, this is the healthy signal, this is the faulty signal, and the faulty signal is something like that. Or some statistical parameters you can find out and then differentiate between the healthy and faulty. So very simple and initial technique, the time domain signal. Some drawbacks also. So I will explain what drawback of the time domain signal in the frequency domain. Frequency domain, again. And one other thing, time frequency analysis. This is the graph between the time and frequency. Okay. This will also some advantage over the frequency domain or time domain signals. Okay, so I will explain some of these in short notes. Also, the fault diagnosis based on artificial intelligence. Now, I think that something research is going on because we are the mechanical engineering, so we are not much familiar about these programming languages. But if you collaborate some project on the fault diagnosis with computer science faculties. Okay, so they will very well know the artificial intelligence, how they are working. Okay, so support vector machines, many people are publishing, means developing that support vector machines also, the programming, and we are using these techniques for the fault diagnosis. Some classifications are there, and we classify the fault, different type of fault. ANN, artificial neural network, deep neural network. So these are the techniques which are currently the fault diagnosis persons are very interested. Okay, so well, we will not cover these techniques, but the time domain frequency and time frequency domains I will explain you. Okay, so in the next slide, the Fourier analysis. Basically, if you just start the vibration signals in the first chapter, you will see what type of vibration signals is there. Okay, so basically in the Fourier has explained about these signals which comprise from cos and sine functions. They combined in this manner, and some coefficients are there, so 0, AF, DF. Okay, so these are this is the formula. Everybody know the Fourier, the time domain signal of the according to the Fourier. Okay, Fourier analysis. So in the frequency analysis, sorry, in the frequency analysis, what you will do, you do the Fourier transform. Okay, so if you if you have signal, if you are simulating these signals, then it's from the Fourier series. But in the actual, if you are capturing the vibration from the machinery, okay, that is may not be related to the Fourier series, but okay, these signals you can approximately say that okay, so this is the following the Fourier series analysis. Okay, so whatever the signal you have a FT, some displacement signals is there. Okay, so by this integration formula, you can convert this into the frequency domain. Okay, so an inverse Fourier transform, that frequency domain you back convert to your original signal and the time domain signal. Okay, so suppose this is one, that arrow is point. This is the next signal. Okay, so we can say this is the something, the combination of the X, Y, Z signals, three signals have a different frequencies. Okay, they combine into this signal. So this will show you the time domain signal. Okay, so the combined time domain signal. If you do the Fourier transform of signals, so you will see that the three frequencies are separately shown here with amplitude. Okay, so whatever the frequency of X signal, what is the frequency of Y signal, and what is the frequency of Z signal. Okay, so the higher frequency of a Z signal is showing on the frequency axis at far away. Okay, so this is the Fourier frequency analysis, how the time domain signal you will convert into the frequency domain. Electrical persons, I think they will know very well about this. Drawback of Fourier analysis. In the Fourier analysis, you see this is the amplitude and the horizontal axis is the frequency. Okay, so I am talking about this below. What is this? Cursor I am going here. The amplitude on the vertical axis and frequency on the horizontal axis. So from this figure, if you get this figure, okay, so you will see here that is not some information about the time, at what time that signals are representing. We are missing here. The time is missing here. Okay, so we can say some drawbacks. Yeah, Fourier analysis, sine and cosine function are used for basic functions. Okay, sine wave, you know, this is the sine wave. For simplicity, the vibrations also we can say the sine wave. The vibrations is in the form of sine wave. Okay, but the in actual some rectangular pulses will be there. Okay, and the Fourier analysis could not represent the time domain information. So I'm talking about the time, at how much time you are taking the signal, okay, at what time the signal have a peak, okay. So this time domain and this is the frequency domain. In the time the frequency domain, we miss the time information. This is the drawback. So what we will do? So short time Fourier transform we will apply. Okay, so this is um, time frequency analysis. Something is here. Yes. One thing is in the time domain signal. Okay, so on the horizontal axis, time is there. On the vertical axis, amplitude. In frequency domain, horizontal axis, the frequency, amplitude, and time frequency, the graph between the time and frequency. Okay, so the short time for transform, we apply. Yeah, slide number 90. So how you overcome this information about the time? Procedure for computing FTFT is to divide a longer time signal into shorter segments. Okay, into shorter segments. How? Divide in a. These are the simple small windows like this. This is the signal. Okay, so we multiplying the Fourier transform over a small window and translate it into the time domain. Okay, so the basic formula is there, something time delay or time some advance will be there, but in the graphical form, in the right hand side you will see the vertical axis the frequency and the horizontal axis is the time. Okay, so you are dividing the frequency and time. Suppose some resolution is there, the comparison is resolution. Left hand side the time resolution is very good. Okay, but frequency resolution is very low. Time resolution is very good. In this right figure, okay, so the frequency resolution is also good. So this is how you will plot, and in the color form you can see at what time that what frequency is occurred, and after this what frequency is occurred, what frequency. So this is the time information also you can see. Okay, and this red and blue, this is showing the amplitude. Okay, so in the right hand side one strip is there. So this amplitude showing the amplitude. The red one is I think highest amplitude. Okay, what frequency the amplitude is there, and what time that frequency and amplitude is occurred. Okay, so segment. This reveals the Fourier spectrum on each shorter segment. Okay, one then usually plots changing spectra on a function of time. Spectrogram, and it is known as a spectrogram, okay? Time frequency graph or waterfall plot. Short time. Now you can see also for short time means 25 seconds, 125 seconds, 375 seconds. You can plot, then you can see if this 25 milliseconds, that means something the frequency is similar. If you are 1000 milliseconds, then the frequency is very strict. You can see at this frequency the amplitude is this. Okay, so you can change this according to your, but many signal processing is required. So if you are good in the signal processing, then you can play with these signals. Okay. Third one is the time frequency, the Beyblade transform. Okay, so some advantage of the Beyblade transform also over the short time Fourier transform. So in the short time Fourier transform, the problem is resolution of the frequency. Yes, sir. That is all. So, okay, the resolution is not good in this case. So, in the Beyblade transform, generally the advantage the drawback of short time Fourier transform is the reason or the creation of the Beyblade transform, okay, and multi-resolution analysis. So it gives good time resolution and high frequency event and good frequency resolution or low frequency event, a combination best suited for many real signals. Beyblade, what is Beyblade? So electrical persons, I think very well known what is Beyblade, but for mechanical engineering students, generally they maybe heard about the Beyblades, but very difficult to analyze in some MATLAB form or some signals. If they have a signal, if you talk about how we will transform that with the help of Beyblade transform, so it's very difficult. Okay, but for basic understanding, I'm explaining here. So it's a small Beyblade signal. Suppose in the right hand, you can see this short, short wave and high amplitude. So this is something function like t minus d upon d. So t is the time, d is the time shift scale, and a is the scaling parameter. So d is the shifting parameter, time shifting parameter, and a is the scaling parameter. So these two, v and a, these the key point of the Beyblade transform. So for A, suppose you are doing scaling at two times you are doing the scaling. So the in the time shifting, you overflow the this small Beyblade over the whole signal up to that time. Okay. Then again, this graph you can see. I can explain it properly. Scale and time. Okay. So if D is changing, that means you are changing the scaling. Okay, A is changing means the particular Beyblade you are um, flowing over the signal, flowing over the time. Okay, so you will get a new signal, and your graph will be the scale versus time. You can see here at the lower, the highest frequency is going, and on the upper side, the lowest frequency is going. Okay, so in the next slide, we will clearly. Okay. Different time frequency style location of the three transforms. So if you just basic understanding about the what is going in the time domain, what is going in the frequency domain, what is going we are applying short time Fourier transform, why we are applying Beyblade transform, why we are applying the Beyblade transform, and other many signal processing techniques are there. If you are very known that if you are doing subject Fourier transform, this is the time and different frequencies are there. Okay, the time is particular duration is fixed, but different frequencies you will get.
Can
In
you
time
repeat
frequency,
what you just, sir, can you repeat what you just said 5 minutes, 1 minute before, because your audio was not coming. So I just missed that part.
okay, so on the slide number 22.
Beginning of this slide, your audio was not coming, so I just missed that part.
Okay, so this is 22 slides.
One only.
Okay, so this is the showing the different types of tile allocations. Means what the result is shown in the time domain series, in the frequency domain series, short time Fourier transform, or in the Beyblade transform. Okay, so in simple time domain signals, some particular time is there and some frequency, whatever the frequency is there. Okay, so in the frequency is there is particular time. in the Fourier transform, you will see different frequencies. So you can see that, okay, this is the frequency and this amplitude. So this is the two-dimensional case. The third dimension is the, suppose, vertical from the screen. That is the amplitude. Okay. So in the third direction, the amplitude is there. But in the two-dimensional case, you can see the Fourier transform at what frequency the amplitude will be there. And this is the time. So time domain is fixed, but the different frequencies you can analyze. In short-time frequency domain, the different frequencies at different time levels you can analyze. So short time Fourier transform is there, something 4x4 is block is there, but at particular time there is a single frequency. And different, suppose this is the time band, and what is the frequency band, and this is the time. But in the wavelet transform, you can see at that particular time there is a different frequency. Okay, so in the top you can see the higher frequencies are showing, and in the lower there is a low frequency. This graph is, I think, this graph is showing higher frequency at the lower, and this frequency is showing higher on the upper, because this is the frequency time graph in the wavelet transform, and this is the scale versus time. Okay, so scale is inversely proportional to the frequency. So if the scale is higher, that means frequency is low. If scale is low, that means frequency is higher. So this graph is showing the scale versus time, and this graph is showing the frequency versus time. Okay, so in the wavelet transform, something is graph is there. On the single graph, you can see different frequencies at particular time, and what are the higher frequencies, what are the lower frequencies, you can analyze the wavelet transform. Okay, so after knowing this time domain signal, frequency domain, and time frequency domain signal, the next thing is the fault diagnosis. How will we do fault diagnosis? Okay, so in the gear fault detection, the mechanical engineers are very well known about the gears, but in electrical persons also, I think they are familiar with the gears, but not the terminology. I will explain something about the terminology also. But fault detection of gear is usually performed by vibration signals. Okay, where other techniques, the advantage of this vibration analysis is the detection of the fault in the gear. So this is very important. Frequency of vibration signal are determined by speed and tooth number. So I'm talking about the suppose you are doing the frequency analysis. Okay. So time information is missing in the frequency domain. Okay. So if we are thinking about the gears, these are the gears in the figure. One is small gear and one is the larger gear. So small gear is generally termed as the pinion, and this is the gear. If we are talking about the revolution, so 3 revolutions per second, and the larger gear is 2 revolutions per second. Okay, so these are we can say this is the frequency, and the bigger gear has 30 teeth, and the smaller gear has 20 teeth. Okay, so between these two, this is how the one tooth is meshing, and how after what time they are repeating. So the common frequency is the mesh frequency. At what time they are meshing? What per second means how many times in a per second they are meshing. This is something mesh frequency, 60 Hz. How you are calculating this? This is T and F. T into F. T is the number of teeth and F the frequency. Okay, so it's a revolution per second, is a revolution per minute is there. Then RPM you can put here in the per second. Hertz, if you are going to calculate in the hertz, generally the signals is in the hertz, not in the RPM. Okay, so hertz you are calculating the hertz, but you can see if we are diagnosing the fault for a small gear or for the larger gear, the max frequency is 10, 60 hertz. Understand what I am saying? Suppose the fault is in the small gear and the max frequency is 60 hertz. So if you are capturing the time domain signal and transform the Fourier transform, so it is in the frequency domain. Okay, so in the frequency domain, we are thinking about the 60 hertz frequency. At 60 hertz frequency, some peak will be there if there is a fault in the gear. But the fault is in the small gear. How you will decide this? Okay, how you will decide this? And the fault is in the larger gear here, then also it's a problem, isn't it? So, so you have to calculate the time because frequency is same. As frequency is same for both the gears, but the time period is different. Time period is the opposite of time period is the inverse of the frequency. Okay, so if there is a 3 revolution per second, if the frequency is there, so its time period will be according to. Okay, and this is also, so the time period for gear 1 and time period for gear 2 is different because the larger gear will take larger time. Okay, and the lower gear one has a small time period. Okay, so the time period information is here, but in the frequency domain you are capturing. So in the case, you know that time, that what time the frequency is here. So I think that the frequency is 60 hertz. Okay, so the frequency is 60 hertz and the number of teeth is 30. Okay, so your period will be T upon F. Upon F, that is the period. So upon F T is 30 by 60. So that is the 0.5 seconds. Okay. So if you are calculating for the small gear, so that is or 20 by 60 will be there. So time period. So this is the graph. This graph is showing in the red color. That's 30 T. This is for the larger gear. So the time period is 0.5 seconds. Okay. So the peaks are there, but if the peaks are suppose we are calculating 20 by 60, okay, so something period will be 30 by 60, 20, so will be less. Okay, so the time period will be less for a small layer, so the time period in the signal will be less. So with the help of this time period analysis, you can see the fault is in the larger gear or the fault is in the lower gear. If you are not calculating the time period, then the 60 hertz frequency is there, and that 60 hertz frequency will give you the indication of the fault, but you are not able to detect in the larger gear the fault is there or in the lower the fault is there. Okay, so in the gear fault diagnosis, in ideal case, fault detection could be done by calculating peak to peak RMS kurtosis of the measured vibration signal. You will measure the time domain signal, just calculate peak to peak, means the healthy gear peak was there and the faulty gear peak. If peak are increasing, then something is wrong. RMS value, okay, RMS value is the energy of the signal they are indicating. So, and the faulty and healthy, you can compare the RMS value. Kurtosis, okay. Kurtosis also you can do for the degrees of the distribution. Okay, so what the peakiness of the distribution, and also compare with the normal distribution. So you can do the analysis with the statistical parameters for this. Okay, so in practical case, however, it is not possible due to noise. The noise is there from other elements. Frequency analysis is done. So in time domain, generally the limited problem. You can just calculate the RMS any times. The RMS value is not predicting because the noise is there. So the faulty signal and handy signal are something very less different. Okay. So in that case, the statistical parameters are not well suited. Okay. So frequency domain analysis. Then in the frequency domain, you know the different signal processing techniques. You can denoising the signals, okay, and you can analyze. Statistical parameters, this is the RMS, so you can measure in any book, you can see these are the statistical parameters. Variance is there, absolute mean is there, mean, RMS, this is the dimensional statistical parameters for the discrete time series. Non-dimensional features of a time waveform. Non-dimensional, you can also put a crest factor, okay, a peak value upon RMS value you can see here. So crest factor, the peak value is there. So if something impact is there, the peak value will be higher. Okay, so the impacting is there, the crest factor will be a good indicator for that. Okay, impulsive factors also for this, clearance factor, shape factor, skewness, okay, for the distribution, kurtosis, you can see these are some parameters. Also, generally we are using the time domain form. Just start the fault diagnosis analysis, just capture the time domain signal and then calculate some statistical parameters for healthy as well as faulty and compare these. Plot in the graph. Okay, I will show you some graphs about these in the last. So in the papers also, if you are doing the research, okay, so the main problem is the signal. Signal you can capture with the help of accelerometer. Okay, experimentally if you are doing this is experimentally on the machine. Okay, generally, or you can do this experiment in your laboratory. Okay, but if you are indicating that these factors, okay, I am not going to industry or not going to perform any experiment, but I want to analyze these parameters for a specific fault, simulations by simulations. Okay, so in this case, some dynamic modeling will be there. I will explain how the simulated signals will be there and you apply these techniques. So in simulation form, you have to simulate some fault, predefine some fault. So you have an indicator that if tooth missing is there, this type of signal will be there. If crack is there in the tooth, this type of signal will be there. If some pitting on the tooth is there, this type of signal is in there. Okay, so by simulation, you are well known previously. Accordingly means for you can understand. And after that, if you doing the experiment, okay, and you see, okay, this type of simulation showing that this is the case of this type of signal is the case of cracked gear. Okay, so after that, the experimental and your simulation both results you can compare also. Okay, so in the frequency domain, fault diagnosis is what the gear mass frequency I have already explained. In frequency domain, you have a gear mass frequency. Okay, so in this case, suppose gear mass frequency is 500, and some simulated signal we are taking here, Fourier transform like sine and cosine. So 500, then ugly, then next frequency 1000, next frequency 15. Okay, so these are the multiples of the frequency. These are the harmonics. So if you see some harmonics, means you are healthy, here is there, okay, healthy here is there, and frequency distribution is there. But at you have to analyze up to some means up to some harmonics. Okay, so here we are talking about the three harmonics, but you can go for fourth, fifth harmonics because some information in the hide in the suppose fifth harmonic also. Okay, so you can analyze for that, but mainly in the first two three harmonics will be sufficient for your analysis purpose. So if you see here, suppose 500 at 500 hertz, the frequency is there. Okay, this is the max frequency, and then next harmonics at 1000, next harmonics at 1500, and okay, only three is there. So time domain signal is there, frequency domain signal is there. If we are considering fault, then this is a distributed, some local, and you will see some sidebands is also there. Okay, so these are the sidebands which are the good indicator for fault. If some sidebands are coming, that you have to analyze the sidebands also. So some fault will be there. This is in the gear or shaft will be there. Okay, so that you have to know that frequency. Okay, gear is there, the max frequency is there. Suppose one gear pair is there, two gear only, but in the gearbox different combinations of the gear. Okay, one stage, two stage, three stage, like that. So there is a different frequency, it's different mass frequency for a separate train. Okay, so there is very lengthy process, but for initially you can consider for a single stage gear, the two gear is there, single mass frequency is there, and it's harmonic. So in the frequency domain you can see their harmonics also and the changes in the normal and faulty. Okay, so these are that's previously known as the stationary signals. Non-stationary gear signals is also the non-stationary means they are changing with time. Okay, if the signal is changing, generally if you are capturing the signals on a machine, they are not they are non-stationary because if you are simulating the signals, they are stationary because you are giving the value something. Okay, so time is fixed at particular time, this amplitude at particular time at this amplitude, this the amplitude is not क्या बोलना चाहिए, that amplitude varying, amplitude is not amplitude is varying, but it's at a particular time interval it's repeating. Okay, but in non-stationary signals, with time, the signals are changing, or in actual practice, actually the non-stationary signal. So this signal is for stationary signals, very easy for analyzing. Non-stationary signals have in the practical use. Okay, so by fluctuating 10% speed, there is no harmonic. You cannot analyze some harmonics or you can see some signal, some mixing type is there. Okay, in faulty signal you can see there is some peak. No, not peak. You cannot see the what frequency and what amplitude are changing. But in a stationary signal, you can see at what frequency and what amplitude is there. Okay, so non-stationary signals, the, you have to work on that. Okay, so some research papers is also coming on the non-stationary signals, different signal processing techniques researchers are applying. Okay, so how to analyze the non-stationary signals for the fault diagnosis technique. Okay, so another case is planetary gear. This I have explained earlier that the stages are different stages are there. If the single stage, double stage, that is also easier than the planetary gear. Okay, some simulated signals are there. If the signals are, you can see many frequencies in frequency domain, you can see many frequencies for a particular gear pair. You cannot see the particular fashion. Even this is a simulated signal. Okay, simulated signal means generally you are considering in the stationary signal. If they are a non-stationary signal, then the very confusing there. But by seeing these figures, you cannot predict what is the fault. Healthy and faulty, they are looking like same. Okay. So non-stationary signals you have to also analyze. So some signal processing that some Taylor transform and other time domain frequency, time frequency analysis. These techniques we have to apply. Okay. Now the second thing is the bearing fault. Bear fault is there, but the main is one of the element, and second one is the wearing. Wearing is the most commonly felt component. Gear is okay, some fault is also in the gear, but wearing generally fails because the many loads of the whole structure or shaft gear by the bearing. You can see in the gas turbine, these are some bearings, red arrow showing. Some turbine is there. This is not a big, small turbine, it's a very big turbine. So these are forces and under dynamic, under rotating conditions. So some loads is also there. And the bearing is very small. Okay. But that bearing is also, you will decide that at what load, what type of bearing is used. Okay. So the ball bearing you are using or journal bearing you are using. Okay. So for heavy loading, you can use the journal bearing. But in normal cases, and slightly loading, some gearboxes, shaft is small shaft is there. So some ball bearings are there. So the failure of the ball bearing is very critical. You can see the figure. So you can. So I will explain something about this. If you know the terminology of the bearing. Okay. So outer ring and case, inner ring and rolling element. These are the small elements in this outer ring, inner ring, okay, case, and between this case the ball bearing is inserted. Number of balls are there, okay, and these are some applications where the bearings you can use. Some induction motor is there, okay. So induction motor is there. Suppose your shaft, you have to place a shaft. Suppose this is the bearing induction motor figure, okay. Some bearing will be required. Otherwise, friction will be there, heat will generate and cannot survive for much longer time. Power loss is there. So bearing is needed. Okay, so this is some setup at IIT Indore. And the rotor mass in yellow color is separate. So this rotor you can see in the, suppose in the gas turbine, some gas turbine rotor is there. Okay, so rotor is something turbine, you can see turbine is there, okay, and the top and the bearing housing, okay, and accelerometer you are placed here. Okay. This is the accelerometer and you are placed on the top of the bearing housing. This is the motor, electric motor is there, okay. Some controls are there at what speed you are rotating this shaft, okay, and some fault is in the bearing you can analyze. For healthy bearing, first of all take the signals from healthy bearing, then replace this bearing with the faulty bearing, whatever the fault in the outer race, and next time generate the fault in the inner race, and in the next time we generate the fault in the ball bearing, in the balls. Okay, different faults you can insert in the laboratory purpose, and you can see what type of variations in the signal for different faults as compared to the healthy bearing. Okay. Now these are the time domain signal. If you consider and discrete time domain, you can calculate this RMS. Okay.
Sir, I think you have Sir, you have interchanged the formulas of mean and RMS.
Hmm? Yeah. Okay. That is in the mean is the RMS value. Okay. Yeah, it's wrong. Okay, so a mean value, RMS the root mean square. So this is the second one is the RMS value, and the mean is the above. So these are indication statistical parameters. So for whatever the gear fault is there or bearing fault is there, if you have a signal, okay, so statistical parameters you can measure with the help of these parameters. Non-dimensional features and also the crest factor, the same thing, okay, in the previous slide. Fault frequency. If we are doing the fault analysis in the frequency domain, then we have to calculate some frequency. As in the case of gear, the gear mass frequency. Okay? One frequency is there, gear mass frequency. And you see the gear mass frequency in the signals. But in the bearing, there is a different frequency, okay, or we can say the fault frequency. Ball pass frequency, outer race. Okay, so for this some formula is there for empirical relation. Ball pass frequency for inner race, fundamental train frequency, ball spin frequency. Okay, so in this parameter, small n is the number of balls. Okay, so in bearing, number of balls, how many balls is there? Okay, frequency for the your shaft speed is okay. So in RPM generally, so you just convert into the hertz. Okay, so you can see in the hertz form, so frequency analysis there, but it is the speed of the shaft. Then D upon capital D, small d is the diameter of the ball, and capital D is the center diameter. In figure you can see for at this corner, for one corner to second corner. Okay, so that is the outer so diameter, mean diameter of the bearing. And alpha is what? The direction of load. Why it is? Because generally bearings the alpha should be 0, I think. Okay, but in many cases, if the speed is changing, so the bearing is straight like that. So small alpha will be there. Okay, if alpha is 0, then okay, put cos 0, cos 0 is 1. This is simple formula is there, 1 minus d by d. So, but in this category, they analyze if something is misaligned in the load, not in the vertical direction, some alpha will be there. So these are the frequencies you calculate initially for your healthy bearing, okay, and then this is the result. So in the time domain signal, you see, okay, time domain signal is there. You can calculate the some statistical parameters for healthy and faulty and see what is the difference. In frequency domain, here is this ball pass frequency for outer range. These are some frequency points are there. Okay, so add these frequency and their harmonics. Okay, so some frequencies are there and their harmonics are there. So you can analyze the okay, the fault is in the outer range. Okay, and some frequencies if we are calculating, suppose more than 500, so they are coming in the next slide. So in the for the inner race also, for ball bearings also. Okay, so different frequencies for we analyze all these frequencies. These are the frequencies. Okay, and what are the changes at what frequency is there in the faulty case? So you can see the fault is in the outer race, or the fault is in the inner race, or the fault is in the ball. Okay, so this is the basic concept. How you analyze the fault bearing, and with the help of mass frequency, how you analyze the fault in the gear. Okay, so these are the also. Now, previously I talked about the experimental measurement of the analysis for the gearbox. Some researchers also identifying by the simulated signal. Then how you will get simulated signal for the gearbox? Okay. So in this case, gearbox dynamic modeling and simulations is there. So you can see there is a single stage gearbox. Okay, so these circles IP, IG. Okay, so these are the moment of inertia for pinion, P is for pinion, G for gear. Two gears are there, and these are connected with this Km and Cm. Okay, Km is the gear mass stiffness, and Cm is the damping, mass damping factor. And in the K by P, KXP, these are the gearing stiffnesses. Okay, because these gears is there. This gear is one shaft is there. Okay, and one shaft is in the gear. This shaft is rested on some bearing housing. Okay, so these are the reactions at the bearing housing. KXP and K by P, both directions. Okay, in horizontal or in vertical. So these are the two reactions to the whatever the stiffness of this structure. Previously you have to define this what is the stiffness of this particular housing and what is the damping of that particular housing. Some oil is there also, so that damping considered is also considered, and some material damping is also there. So the model you have to lump parameter model is there for the gear housing, so stiffness and damping parameter. And same thing for the gear and pinion. The very interesting point is there, these two gears are matching at teeth. Okay, so mass stiffness is the combined tooth stiffness. Okay, whatever the tooth is there, if a single teeth is there to apply in machine design, you will see the gear tooth we can consider as a cantilever beam, apply some load. Okay, so that's the case. If some cantilever beam is considering means some stiffness of that tooth, you have to measure. But in the dynamic model, this bearing housing stiffnesses are constant, or you can consider as a constant. Okay, very little variation will be there. But if our material are simultaneously, all things are there, then you can consider that bearing housing stiffnesses are constant. Okay, but this gear mass stiffness, this is not constant during the rotation of the gear. Okay, gears are rotating, but the mass stiffness is not constant. At particular moment, the mass stiffness is something. Then the gear is rotated, the mass stiffness is changed. So in the dynamic model, this is the dynamic model, and you write these are the differential equations for this. Okay, so these are the differential equations, and by any method you will solve this xp or x by p. These are replacement. After that, velocity or acceleration you can find out. But basically, this is the 6th degree of freedom of a single gear pair model, and these are the differential equations. Okay, but I am just focusing the point is on the gear mass stiffness, because everything in the gear model is under observation. Okay, but the mass stiffness variation you have to put. Many researchers initially developed the dynamic model, and they consider the mass stiffness. Okay, it's a stiffness, and they consider the average or something. Okay, so this is a particular value, and in the dynamic model, these are equations. Okay, so in these equations, in the here, this is Km. So they put constant value of this mass stiffness. If you are putting the constant value of this mass stiffness, then whole thing is very easy. Just write the differential equations, solve them by Runge-Kutta method or whatever the processing is there. Okay, just solve by numerical method and find out the displacement. a particular direction, whatever in the y direction or in the x direction, and you have a signal, vibration signal, then apply some signal processing techniques. But the case is gear mass stiffness, and many researchers are doing their best for calculating the gear mass stiffness. Gears are very complicated structure, and in macro level you can see there is not a much difference, but in the micro level you finding the fault, you have to know at what rotation at what time, at what rotation of the gear, what is the value of mass stiffness. Plot you can see in the figure. Okay, and one thing is there, during the massing only two teeth are not in the engage. For some time two teeth are in the engage, but for some time four teeth are in the engagement. If two teeth are in the engagement, then there is a two stiffness, one for gear teeth stiffness and one for pinion teeth stiffness, and both are in the series combination. So you know the combined stiffness in the series, if you are connected the two springs in the series, then K1 K2 upon K1 plus K2 is the equivalent stiffness. If the two gear are matching, two teeth are matching, that means K1 K2 by K1 plus K2. This is the mass stiffness. But for four teeth are in engagement, yeah, two pair. So for one pair, K1 K2 upon K1 plus K2. Second pair, K1 K2 upon K1 plus K2, and these two are connected in the parallel case. So something is there in the graph, you can understand at point A, double tooth contact pair, DTCT, double tooth contact pair, means four teeth are involved. Okay, so at zero angular displacement, the mass stiffness at A point 10 into 10 raised to power 8 Newton per meter. Then the rotation of the angular gear will be there. So it varies from A to B. Then STCT, single tooth contact pair, means only two teeth are involved. Single tooth, matlab the one tooth of the gear and one tooth of the pinion. Two teeth are there. So STCT. Okay, so DTCT to STCT, there is a changing four teeth to two teeth. Okay, so two pairs to one pair. There is a sudden drop B to C. If the mass stiffness is suddenly changing from B to C, there will be a jerk in the gear pair. So this is the root cause of the vibration of the gear. Because in the fault diagnosis, we are interested in the root cause. So we analyze that mass stiffness is the root cause because it changed from B to C. But it's for case for healthy gear also. And what happens if some crack will be there or some pitting will be there on the tooth? This is the case for healthy gear. A to B, B to C, sudden drop. Then single tooth to double tooth, D to E, that is a single sudden rise. This is for the case of healthy gear. That means in healthy gears, the gearbox is vibrating because the stiffness is changing. And stiffness in the differential equation is involved. So the mass stiffness is changed, the vibration signals will be changed. Okay, so the vibration signal is very much responsible for stiffness, that mass stiffness. So model for the gear mass stiffness, it's cracked in some these are some formulas. You can refer some research papers. You can see here the different modeling of the mass stiffness is there. KB the bending stiffness, K is the shear stiffness, Ka is the axial stiffness, K as the Hertzian contact stiffness. and Kf is the flat foundation stiffness. So these are some formulas we are derived for. This is a very complicated structure of steel that we have to, because it's some involute profile is there. Okay, so some force analysis is also very big task in this case, because the force is moving from bottom to top of the teeth. Okay, so these are the mass stiffness component, and you have to arrange into the series parallel combination. So the combined stiffness is termed as mass stiffness. This is Km is the gear mass stiffness, and these are the components. So one indicating for pinion gear and two indicating for gear. So two pairs is there in the upper formula, and the below formula I122 means this whole formula is for one pair plus whole formula for second pair. Okay, so this is for double tooth contact pair. Now, if there is a crack in the fault, so the bending stiffness for crack and shear stiffness for crack, you have modeled it, and Q1 is the crack length. Okay, so at the tooth root, the stress concentration is very high at the tooth root of the gear. So the crack will initiate at that point, and if you initially, because you are simulating signals, so you put some 0.1 mm or 1 mm, 2 mm, okay, this crack length, and you calculate the bending stiffness and shear stiffness will change. Okay, so you put this faulty gear in this signal, so you will get the vibration signal for the faulty gear. This is the whole picture of this. Now, the simulated gear mass stiffness with variation of the gear fault. Okay, I'm forgetting about the mentioning the fault. So some graph is there. In the healthy case, there is a something is this, but if crack root crack is there, the stiffness is dipping, lowering the stiffness. That means if healthy case, some stiffness is varying from 0 to 18. So this is the rotation degree of the gear. If crack is there, the stiffness is also changing. In healthy case, it is changing. Okay, but if fault is there, the stiffness is also changing. Okay, whether it is the swelling on the tooth, stiffness will change. Crack on the tooth, stiffness will change. Tooth missing is there, stiffness will change as particular rotation of the angle. Okay, so this is the you can consider is a rotational angle into time domain. Okay, so because this is the rotation of the angle, so in time you can convert. So this mass stiffness variation with time, it is also known as, that's why, the time varying mass stiffness, because it is changing during the time. So this time varying mass stiffness, you have to put the differential equation, and you will get the simulated signal accurately accordingly. And you will see that if the crack is there, what type of signal is changing. So without experiment, you are just known about the okay, the crack will be there, this type of signal will be changed. If ear tooth missing is there, this type of signal will be changed. Okay, so in the simulation, without any big cost for doing the experiment, you will get the signals and predict and publish. If we are doing, suppose some people are doing wrong modeling, 6 degree of freedom modeling you can do for 8 degree of freedom modeling, 16 degree of freedom modeling, and people are doing 16 degree of freedom of a single sphere box. They are doing the research on that. Okay, so if you are because the degree of freedom is in your hand, if you are reducing the degree of freedom of a gear system, that means you are approaching inaccurate results. You are increasing the degree of freedom, you are increasing the accuracy. Okay, Now the mass stiffness analytically, you see what different type of modeling is there, stiffness component is there, some experimental methods also there. You can measure this mass stiffness experimentally and put in the dynamic model accordingly, or you can see some costly is there. Okay, so doing some experiment for calculating the gear mass stiffness, but doing the experiment and compare that analytical model. Okay, you will see some differences and correlation. Okay, so some photoelasticity techniques there. You can make some gears, polycarbonate gears will be there. Okay, applied some load and fringes will be there. These are the isochromatic fringe patterns are there. And with the help of these isochromatic fringe patterns, you will get the stress level. Okay, and for crack, that stress intensity factors you can calculate, and the crack opening displacement you can calculate. So with the help of this, the stiffness. Okay, so in the terms of stresses and some combination of the analytical methods also, not the mass stiffness purely you are calculating from the experimentally by the photoelasticity, but analytical combination of the analytical method, you will get the stiffness for the gear by doing the experiment. And the experimental results is also you can see here. Second one, strain gauge. So same thing is calculating the strain at the tooth level. Okay, these are the some setups. Okay, so in for capturing the strain gauge data is also some LabVIEW programming is also required for if you are considering some NI instrument for that. Otherwise, you have to develop the whole system, or ready-made software you have to purchase for that. So these are the healthy gear, and some crack information will be there, and mass stiffness variation you can see. Laser displacement sensor, and directly you can calculate the displacement of the tooth. Okay, so for particular tooth deflection you can measure, and then combine that mass stiffness for gear 1 and gear 2, and accordingly you can plot the gear mass stiffness. These are the things. Digital image correlation. So again, this is the whole field analysis technique. So high camera I have used, but CCD camera you can use for this purpose, and capturing some frames per second. Okay, so that images you have to analyze on some MATLAB software or some other coding. Okay, so and analyze the what type of displacement of the gears will be there, or strain, whatever the stress and strain analysis you can do, and displacement analysis also you can do. Okay, so by knowing the force from engagement to disengagement, the force distribution is also different. Okay, so by considering this, you can measure the mass stiffness. Some preparation of the specimen required, some random speckles have to speckle on this. First of all, you paint the gears, then speckle some patterns, capture the images, then rotate the gear for particular position, then apply the load. Okay, you will get the mass stiffness result. Experimental model analysis also you can do. Okay, so in the experimental model analysis, this is a model analysis, okay, whatever frequency mode shapes you will get in the model analysis. In experimental model analysis, okay, in model analysis, what you will do analytically, generally in vibration analysis, the model analysis is there. Model analysis in what? If you know the mass stiffness, means you know the mass stiffness, you know the bearing stiffness, you know the damping factor, you know all the constants, then modal analysis will give you the natural frequencies and mode shapes accordingly. But in experimental modal analysis, you don't know, I mean, you don't need the stiffness values, because your system is there, you placing the accelerometer, okay, and capturing the signal, vibration signal, and by impact hammer. Modal analysis is done by the impact hammer test. So in the modal analysis, we'll get the real and imaginary FRF plot, frequency response plot. So with the help of these frequency response plots, you back to the stiffness matrices. I will show you how the stiffness matrices we will get. These are the setup. Okay. These are the stiffness matrices. Suppose the stiffness matrix we am focusing here. It is K plus Km. Km is stiffness. Km, Km, Km. This is the symmetric stiffness matrix is there. And I am considering a 2 degree of freedom. Suppose here. So 2 degree of freedom spring mass system is there. Okay. And compare that experimental result up to the two frequencies, two natural frequencies. Okay. So at first natural frequency, whatever the parameters we will get from FRF plot. For second natural frequencies, these are the FRF plots. Okay, so I am considering only 2 degree of freedom. So first peak, the first degree of, second is second degree of freedom. So these are the some parameters. Okay, FRF plots, frequency response functions. So these are the used for calculating this stiffness matrix. So with the experiment, you will get this system and compare that K11, K12, K21, K22. This is the matrix. So compare that K11 means K plus Km equal to what the value experimentally you will get. Okay, and this K is the varying stiffness. So you have to some put that varying stiffness and you will get the mass stiffness. So some stiffnesses you have to know because your system is there. So you know the approximate stiffness of that particular, but mass stiffness you will not know. Okay, sorry. So mass stiffness matrix, analytically you know, or experimental you know this data and compare, then mass stiffness you will calculate. And these are the results for this experimental. Because of the time limitation, I am just completing this. Now the simulated signals. So these mass stiffness value you just put in the dynamic model and solve these differential equations by some Rangakutta method and you will get the by displacement with respect to time. Okay, so these are the results. And you can convert into the frequency domain also and analyze some signal processing techniques or statistical parameters. You can compare that kurtosis, RMS, how they are changing by increasing the crack length. Okay, so you can this type of analysis can be done. There are some references. Thank you for your valuable time. Okay, now I'm coming.
Hello.
Okay. Hello. Yes.
Uh,
I'm switching on my video.
yes, sir.
Yes, sir. Okay, so if you have some questions, you can ask me.
Any questions from the participants?
Hello.
Yes. Hello.
Is it audible, sir?
Yes, sir.
Okay, one question I would like to ask from your slide number 38.
Slide number 38.
Yes, sir. 38 and 39.
Okay. Okay. Yes.
Sir, here you are calculating the gear mesh stiffness with the crack in one tooth, right?
Yes. Yes. Yes.
Okay. And in the previous slide, you have just shown the 2 point and 4 points like contact in the gear. Just
Yes.
previous
This
30.
one.
Yes.
This one.
Just yes, sir. Yes, sir. So DTCP and STCP you are calculating. So very
Yes,
basic
yes.
doubt. I just want to ask whether we are considering the effect of backlash here or not in calculating the stiffness.
Back. Yes. Yeah. And this is a model. You are saying that.
Yes, sir.
Okay.
In this
So
mathematical equation,
yeah.
did we
In this
consider the
equation,
yes,
in
sir.
these equations, the backlash contact is not considered. Okay. We are assuming that there is no backlash contact is there. Okay. So if we are actually, the researchers are doing their best on this category. If some researchers is also done, some backlash contact is there. Okay, so some backlash contact there, that means you are increasing some stiffness. So they are considered, one factor is also KB, suppose, for backlash, and they are also connect in this series combination, and we will see the effect of the backlash.
That means this is the standard modeling equations here.
Yeah, these are the standards for bending, shear, and axial. But because in the recent 2004, I think there is not considering the shear effect. Okay, KS.
Yes. Yes.
So in 2008, something Tian, that he's in from Canada, they considered this shear effect. Okay. So okay, next person is going to think about the backlash stiffness is also have to consider. So they introduce one other factor. Okay. If you are have some problem, suppose you are not considering oil. Okay, we are not
Yes, sir.
considering oil in the modeling. So if you consider the stiffness of the oil also, then obviously some result will be deviate, and you can consider in the modeling, and you will get some new paper also you can publish.
Okay, sir. I'm getting your point, sir. I have 2-3 more questions, so I just,
Okay.
with the permission of Dr. Parikshit, sir, he will allow me. We are running out of time, so can I ask?
Yeah.
Yeah. Okay, sir. Sometimes, sir, I have seen on the gear 2 that people are providing some hole or elliptical kind of cavities throughout the gear thickness in order to increase the tooth strength. Like we are considering this tooth as a cantilever beam, and when we are analyzing this tooth, by providing this kind of hole or ellipse, is really the strength is increasing in dynamic operations, or it's just a theory? That is, I just want to ask. Like it is some design modifications I have seen in the literatures. Like people are providing just where we are fixing the base of the cantilever, and just below that, fixed edge, we are providing some hole or ellipse kind of cavity throughout the thickness of the gear disc.
Yeah.
So, like it's kind of providing a tunnel kind of a structure just below the gear tooth.
Actually, if you are inserting some hole, which in actual practice there is a gear, and some hole or cavity will be there in the body.
Yes.
Okay, so this is the last equation you are saying, KF is there. Last equation, KF.
Yes, sir. 1 by KF.
1 by KF. This is the flat foundation stiffness. So some researchers, this is developed analytically for the flat surface. This is the rim. The shaft hole is there only, but the whole structure is planned. If you are considering some another hole on the flat, you have to modify this equation.
Yeah, that I agree, sir. But my question is just basic question. Just below this fixed edge, if you can, I can see your gear too. The fixed edge, just below the fixed edge, if I am providing some structural hole and cavity, like, so that means we are basically removing the material from the disc just below the gear throughout the thickness. So, or in other words, we are providing some tunnel, or you can say, hole cavity kind of thing. So, is it significantly? Is it increasing the strength in power transmission, or is just an
Actually,
hypothesis?
if you are reducing the material, obviously its stiffness is reducing. Okay.
Yes.
If you come remove the material, so the bending
Yes.
stiffness will be lower. Okay, because at that
Bending
time, yeah, bending stiffness will be reduced. So obviously the mass stiffness is reduced. So your tooth is weaker. But for avoiding some interference or something, you have removed that material also. Okay.
Okay. And one last question, sir. Is there any compliance approaches available in the literatures for the calculation of the stiffness? Like, is stiffness,
What?
compliance approaches is under
Yeah.
development for the
Compliance actually, initially the compliance, you have to just the reciprocal of this stiffness. Initially, initially they are calculating from the compliance, and recently also they are calculating. But the stiffness comes, and you are modeling this so easy. But for both ways, you can go whatever you suitable for your analysis. But the results are same.
Okay. Getting, sir. Getting. Thank you, sir. Thank you very much.
Yeah. Okay. Thank you.
Thank you so much, sir, Naresh sir,
Yes,
for
sir.
your session. All the participants must have got tremendous knowledge out of it.
Yes.
So we thank you, everyone. Tomorrow is the last day. So kindly join tomorrow at 9:30. Thank you.
Okay. Thank you, sir.
Thank you, sir.